Hello, my name is Cecil Barnett-Neefs, and in this module I'll be giving an introduction to deploying agent-based models in food safety environments and what to consider when building one. This lecture is the first in a series of presentations on ABMs in food safety. A decision support tool, such as a computer model, can provide useful analysis on how to proceed. One such tool is an agent-based model, or ABM, which simulates multiple autonomous agents within a virtual environment. This allows for the observation of emergent behavior, where an effect can be produced as a result of multiple parts of the model interacting with each other. An ABM can also simulate the consequences of changing one or more components of the model and showing how this ripple effect affects model predictions. A number of different scenarios can be run, allowing users to investigate different interventions, evaluate sampling methods, or in a non-food safety related setting, optimize productivity. To set the scene, say you have a food handling facility such as a packing house or a processing facility. Surfaces, such as equipment components or the hands of employees, may interact both with each other and with food material during normal operations by coming into direct or indirect contact with each other. Facilities like this will typically have a large open room with equipment around it to handle incoming food material, such as produce, with pieces such as flumes, brush beds, and packing areas present. The environment within these areas can vary. Some may be wet, some may have a large number of employees around them, but all will involve physical contact. During operations, there is a risk of pathogens being introduced into a facility and spreading beyond their initial starting point by using this network of contacts. Once within the facility, the pathogen population can get established and persist in the areas where favorable conditions are present. Ultimately, this is a food safety issue, as environmental sources can contaminate finished product. In these scenarios, it can be unclear where the contamination originated from, where it may be persisting, or how to best intervene against it. This uncertainty in how to proceed can be compounded by a lack of information being provided by a facility's environmental monitoring program, as they cannot keep testing every surface present. Within an ABM, the core component is the agent. Each agent can interact with each other. It represents the employees or equipment, having its own behavior rules to act autonomously, such as when to interact with other agents, and will track a number of statistics for later analysis. A key question in ABM development is how you would represent equipment or employees as agents. In this setting, one agent does not always represent the entire piece of equipment, especially with larger and more complex objects, though smaller and simpler objects can be more easily represented as a single agent. Factors to consider in splitting equipment up into separate agents includes hygienic zoning, cleanability, and the overall understanding of their importance in the spread and persistence of pathogens in the facility. Imagine you have a conveyor belt. How would you define the agent? Do you consider the entire machine as one agent? This may be too vague to be useful. What if we break it down into 2 or 3 major components? This is better, but there are still a number of different pieces involved that have been overlooked. Depending on the equipment characteristics and interactions, this piece of equipment could be broken down into at least 4, if not more, agents. 1 for the belt itself, 1 or 2 to represent the motor mechanism, 1 or more for the frame and the housing, and 1 or more for the feet making contact with the ground. An employee, for example, may be represented by agents for hands and an apron. It is important for a model designer to decide how many subcomponents can be represented by one agent. Additionally, other characteristics that need to be set include position, surface area, hygienic zone category, cleanability, and sanitation frequency. The model will then track other values on each agent as part of the simulation, such as the quantity of contamination, duration of contamination, frequency, the water level, the amount of water on a specific agent. In addition to the agents, other data values used in building a model include links between pairs of agents, which include directed links for contact that would allow for contamination spreading only in one direction, sort of a one-way street, and undirected links for contact that would allow two-way transmission of contamination via repeated physical contact or proximity. Facility dimensions, the schedule of activities and the processes of what happens during these events, levels of traffic and water on the facility floor for each event, and sanitation procedures. A full-size operational model can be used as a digital twin of a real food facility to determine a number of key questions regarding the facility. What are the most likely origins of contamination? How pathogens might be moving through the facility, and which surfaces are most likely to be contaminated most of the time? Which methods are predicted to be effective for reducing contamination risks? How might you design an environmental monitoring program to more effectively detect it? How could productivity be optimized? These concepts have been put into action to produce several working agent-based models of Listeria contamination in food handling facilities. Currently, there are 3 sets of ABMs using the environmental monitoring with an agent-based model of Listeria, or Enable. These are built in the NetLogo language. The ABMs built in Enable have been used to investigate several aspects related to Listeria in food processing facilities and packing houses, such as general contamination behavior, designing and assessing sampling strategies, and assessing the performance of intervention strategies. The first model was in a cold smoked salmon facility and used to characterize Listeria contamination behavior. The second was developed for fresh cut produce facilities, and in addition to characterizing Listeria dynamics, also allowed for the testing of different environmental monitoring program strategies. The third model was built for produce packing houses and tested the effectiveness of different hypothetical interventions in reducing Listeria contamination. You can see the individual agents in the image represented by the various shapes and figures, the links between them as interconnecting lines, and the surrounding environment as square patches. In conclusion, agent-based models can be used to create digital twins of existing food processing facilities or packing houses, but require detailed information about those environments in order to be built. However, as we have seen, once up and running, these models are capable of investigating a wide range of different scenarios. Thanks for watching. If you have any further questions, don't hesitate to contact us at the shown email address. Work was supported by the following awards.